Actually, okay, guys, let's get our class started. And you can pick up your quizzes later on your way out. So today I posted the projects. So I posted 2 projects, a simulation projects, by the way. These are fairly simple projects. So you should be able to like do it in fairly short time. The idea is to get you practice on building SPICE models and simulate the performance and then compare with like hand calculations. So for each of the simulations, on project 1, what you need to do is for each one, you should do a hand calculation on each of the questions. So that you get some answers, and then you build your SPICE model and you simulate it. And then you compare the differences. There are always some differences. When you build the SPICE model, you have to find a device that is suitable for you to use. SPICE has a lot of kinds of MOSFETs, BJTs that you can look for. Many of them you're able to go in, change the mu, COX, and W and L, so you can do those. So when you change all those parameters, it hopefully will fit your model. So if they don't give you the right result, which means either you have a wrong device or you have a wrong model, so you have to change the model. But I'm not asking you to get exactly the same result from the simulation and your hand calculation, and it's always very difficult. But if you have a huge difference, let's say you get a gain of 10 in hand calculation, but in the simulation you get gain of 50, that's apparently not okay. But if in a simulation you got 12, even 15, I don't care, okay? So fine. But what you need to do is in explanation, you say, why did I get it like one is 10, but the other one is 15? You want to discuss it. You have a good reason to explain it. That's the important part in the report. Okay, you don't want to get exactly. I mean, if you can, that's fine. You're saying, but you still discuss because it's impossible for your first time to get them right. So you can discuss, this is what I did, and this is what I did, and eventually I got the 2 numbers very close. That's the process that you get. Yeah. Yeah, those are textbook problems. Yeah, just go to each chapter, you get the number, you got the figure, and everything was given. So that's for the first one. Yeah, go ahead. Yeah. Yeah. We have the set voltage and set voltage and then our signals. Yeah, you have to set your own signal, right? Yeah. Right. Yeah. Whatever you make it, yeah. I mean, for example, students started by dragging a voltage source, and you have to define the frequency, and you have to define the amplitude, right? So those are the 2 things. Students said, okay, the default is kind of 1 volt, 1 kilohertz. It doesn't work. You have to change it to millivolts. You have to change it to the frequency. All those things you have to go familiar with. Yeah. Yeah. Right. Right. Yeah, that's true. And the second project is actually, when I taught this class before, it was a hardware like implementation project. But I figured that if we have so many students, it's not very likely possible to get all those hardware available for you. So I thought we'll just do a purely simulation. It's a very fun project. I mean, when you build it, you'll notice that how can you generate an AC sinusoidal waveform, purely AC sinusoidal waveform from a DC power supply. So it's very interesting. But you have to do some adjustment to make it work. It doesn't, you build the circuit, 99% of the time, it doesn't work the first time. So you have to build it quite a few times, adjust values and say, but the circuit is given. So just duplicate the circuit, adjust the values, you're likely to make it work very, very quickly. And then follow the stuff, write your report. This is the individual project because it's so simple. I don't expect you need a lot of help, but feel free to discuss among yourselves. You have a problem, you want to discuss with another person, fine. But eventually, you need to build your own model. In your report, you need to screen capture all those circuits, the output, the curves, the sweep, all the things, paste it onto your own report, and write your own report. Our system will be able to catch you if you simply copy somebody else, because the two figures will be identical. But if you do your own, even if you two talked, the two figures will be different, because everybody's screen capture different size, different angle, it will be different. So if I see two figures are the same, identical, you guys are going to get a 0 on that project. Okay? So that's important. So I don't mind you to discuss, but I do mind if you copy each other. But I want you to do your own report, do your own, eventually understand the simulation by yourself. Again, this is such a simple project. There's no need for you to worry. There's no need for you to copy. It's simply practice your skills, enhance your learning. So do it yourself. Okay? Any questions? Any more questions? Yeah. Yeah. One PDF for all three. Yeah. But write like part 1 and a feature generation part 2. Don't mix them. Yeah. Any other questions? Okay. So I know we're a little bit behind the schedule because some of the contents seem to be more difficult than I have anticipated. So in chapter 10, we originally arranged 6 lectures. I think I would reduce to either 4 or 5, so that will catch up 1. So we're going to skip some of the sections. I'm going to point to you which section we're going to skip. Some of the sections will simply enhance the different analysis method. So even if we skip them, we wouldn't miss too much. We're just missing some of the method, like a constant method, for example. But you'll still be able to analyze it. So that's what we're going to do. And of course, we're going to have a quiz today at the end of the lecture today. So let's get started. So let me start this. Do you have everybody still remembers what is a capacitor? How is a capacitor like made? And what condition would you see as something like a capacitor instead of a resistor? How do you make a capacitor? The two plates close to each other, right? So if you have a two plate, and these two plates, you can be bigger, can be small, and it can be long, can be, different distances. And this place, between these two plates, you will have a capacitance. And the capacitance is there because in the gap, it does not conduct, it does not flow current. You cannot have DC current flowing through the capacitor because in the middle it's barrier, it's air or something else. So between the two plates, there's no continuous current, DC current. But when you put a voltage on this place, so what happens is you see these positive particles are going to accumulate on the positive side, and then the electrons are going to accumulate on the other plate. So when you have this positive and negative plates, it forms electrical field. So there's electrical field in between. So there's E, and the particles, either positive or negative, that's on each surface is called a charge, a Q. So the more Q you have, the stronger the electrical field. Okay? So depending on the place, the size of the place, and then you can calculate how many electrons that can be accumulated on each of these plates. So during the charging process, during the moving, you do see a current. So there's a current, but once the charge is complete, there's no more current. Okay, so for you, do you know when the charge will complete? At what time the current will stop? Charge is full, and then what else? Is the voltage on the plate is the same as the supply voltage. When the voltage is the same, there's no more current. Okay, but when there's a voltage difference, there's charge going through there. So the total capacitance calculation is very simple. It's epsilon R times epsilon air, then times A divided by D. And D is the distance. And A is area. And epsilon 0 is the permittivity of air. And epsilon R is the relative permittivity of media. So which means if you have mica, if you have silicon, you have something that's insulation material, that permittivities can be different from air. You're always higher, but not so much higher, maybe 2 or 3 times higher. And this epsilon, I believe, is something like a very small number. So epsilon is 8.85 times 10 to the minus 12, and the unit is farads per meter. So that's what you get, the capacitance. So this is very important. Anywhere you have 2 plates, you have capacitance. But the capacitance, of course, is not depending on the voltage. So even if you don't have a voltage, the capacitance is still there. Okay. So in circuits, you learn a lot of stuff about circuits. You know, for example, you learned about you probably learn about this. You learn about current. You probably learned the current. What is current? Current in a capacitor equal to C dV dt, right? So that's what you get. When the voltage change, the current is going to increase. When voltage increase, the current is going to increase. And so, well, if the voltage increase linearly, you got constant current. So those are things that you learn. We're not going to talk to that. So when you have a capacitor, it's a better idea to connect a voltage source directly to a capacitor, because the equation that I wrote before is going to give you some very meaningful reason. So if you connect the voltage source directly to a capacitor, which means the voltage is changing from 0 to a certain voltage in 0 time. So dV over dt is infinity. And dV dt over infinity, your I is infinity. So your circuit is going to blow up. So never connect a capacitor with a voltage source directly. So what you do is you always connect some like resistance. When you connect resistance, and then the circuit is very much different. And when we write the circuit, we can write VI equal to I times R plus C dV over dt times oops, I did it this way. We can do it. We can do it in a way like plus VC, and then VC you can use the upper equation to get like a integration of I C dt. Okay, so that's what we can do. But if this input is a transient signal, you have to do right this way. But if input voltage source is not a DC but a sinusoidal waveform, and then that's where the complex number come in. Remember, we can write this to be I times R plus J omega C, 1 over J omega C times I. So this 1 over J omega C is called impedance. It's the impedance of the capacitor. But that J omega is a complex number. I mean, just give you a review of what we have learned before. But in circuit theory and in controls, when you do 4 time, for example, in a lot of places, having a J omega is a little bit too much. During the process, you have to J square equal to -1 and all that stuff come in. So people said, let's make it simple. Instead of using J omega, we're going to name J omega a name. We'll give it called S. So S becomes J omega, so J omega is S. It's the same thing. So in the future, you saw S. Why is S? S, okay, S is J omega. So why is J omega? J omega is S. It's the same thing. But transferring J omega to S makes a huge difference in the control theory because now you can distinguish zeros and poles and that kind of stuff instead of J omega. So that's the difference. But eventually, you have to convert J omega S into J omega in order to calculate the frequency. So regardless, the end goal is the same. You're going to get to the point. So by replacing S with J omega, we can get VI equal to I times R plus 1 over SC times I. And then we can write VO equal to I times SC. So now we can calculate gain is VO over VI. You remember, gain is output over input. So this is called voltage gain. Now, at the times, like later today, we're going to talk about current gain. That's a different thing, but it's all gain. So sometimes it's current gain, sometimes it's voltage gain. But most of the time, when we talk about gain, if we don't say it, it's a voltage gain. So voltage gain will be, so we can plug in these numbers. We get I times SC over 1 divided by IR plus I over SC. And this I now cancel. So we get 1 over SC divided by R plus 1 over SC. Now we simplify this by multiplying C on both numerator and denominator. We get 1 over 1 plus S times RC. So in this circuit, and you see there's the gain is related to what? To R and C and S. So which means frequency is something here. And we also know that this, what is RC? So RC basically is the time constant, right? So that's what you learn again in circuits. Now we also can get the gain as its absolute value by plugging S equal to J omega. So you can get this to be 1 over square root of 1 plus omega squared RC squared. We got this. So if we plug in this omega as a function of omega, and this is A. So you will get something like this. Okay. But in circuits, what we found is that sometimes we actually want to be able to evaluate, like compare different circuits. I want to use the increase the gain. Basically, so far we have talked a lot about the voltage gain is 10, 100, or 8,000, whatever that gain number is. But in electronics, they actually use a different number. They call it dB. So dB is what they did is they use this body plot. They simply use this as a 20 times log. So just take the gain, get the absolute value, get the logarithm, and then multiply by 20. So this this body plot is very important Like people use this to represent like how many dB of gain. And then if zero, so because in this case, if your gain is 1, if your gain is 1, what will be the dB? 0, right? So 0 corresponding to a gain of 1, which means 0 dB increase, 0 dB decrease. So input come in, input come out, same, no gain. So that's 0 dB. So it's very easy to understand now why they use this, because 0 means no gain, okay, in and out. And if you have a gain of, say, of 10, in this case, you'll be 20 dB of gain, right? Log 10 is 1. So if your gain is 100, you got 40 dB. If your gain is 1,000, it's 60 dB. So every 20 dB means you're increased by 10 times. So now you recall a logarithm plot is every 10, it becomes like equivalent from 0.1 to 1 is same distance from 0.1 to 1, from 1 to 100, 10 to 100. So they can shrink the gain in a linear plot. So that's what this dB can do for you. So for this circuit, we are down here. But if you calculate the, if you plot the gain, and you see what happens when omega equal to 1 over RC. So one omega equal to 1 over RC. And you plug in the number to here. See what do you get? This becomes 1, right? Omega equal 1 over RC, so this is 1. So 1 plus 1 is 2, square root of 2. So A is 1 over square root of 2. So A is 1 over square root of 2. And then in this case, the 20 log will become the 20 log A. 20 log A will become log of 2 is 1.5 times 20. That gives you minus 3 dB. So 3 dB. Minus 3 dB. So when you plot this diagram, it becomes more like this. It more or less constant, and it drops like this. And at this point, 3 dB. And this is omega equal to 1 over RC. And then, so in the future, you will hear this very often. They call it 3 dB. Okay, so 3 dB means there is a gain drop at a little bit, but not too much, but 3 dB drop. And okay, so this is the one for something like, okay, so we get to this point. So what this really means is that when the frequency is extremely low, your gain is almost 0. Right? Because if your frequency is small, if your frequency is very small, and this becomes 0, so 1 plus 1, your gain is 1. So your dB is 0. If your frequency is low. When your frequency increase, when this RC, this omega equal to 1 over RC, it will start to drop to 3 dB over here. So it drops here. So that's why you have 3 dB. So what happens when your omega keep increase? When omega keep increase, this number becomes bigger, right? And this number becomes bigger means A is becoming smaller and smaller. When this is so big that it much larger than 1, what happens? And this 1 is gone, and this much larger because this 1 can be neglected, and you got omega over RC square root, and you take it out, so you get RC over omega. So you got a linear relationship. So basically, when omega is large, the gain and omega has a linear. Yeah, well, it's not linear. It's almost actually it's RC over omega. So it's kind of when you take the dB, it's actually linear. So that's why you have this linear curve. So in the future, you will see a lot of curves like this. They're going to plot the curve. I'm going to plot it here. And this drop, actually, there's 3 dB here. So this is your omega t. That's kind of the 3 dB frequency. And then in this case, there's 0 dB. But in this case, they call it minus 20 dB per decade. What does it mean is that your gain will drop 20 dB for every frequency increase of 10 times. Does it make sense? So your gain is 20. Your gain is 20 times log A, and which is equal to 20 times log so 1 plus omega RC squared. And then when we talk about when omega is small, and this equal to 0 dB. When omega equal to 1 over RC, equal to 3 dB. When omega equal to 10 times RC, and you got so if it's 10 and then 10, so neglect that 1, you got 10 over minus 10, so you got really minus 20 dB. So that's what you get, the minus 20 dB. So that's why, see, for every 10 times increase of frequency, your dB decreased by 20. So that's what they call this line is minus 20 dB per decade. 1 decade means an increase of 10. Okay. So the previous one was so let's go. Well, we don't have to go back. So guys, look at this, which means when frequency is low, you have a gain of 0. You have a dB of 0, but you have a gain of 1, which is fine. But what happens with high frequency, like beyond 10 over RC? It already minus 20 dB. Minus 20 dB means it decreased by 10 times. Every 20 dB is 10. So it decreased by 10 times. So when your frequency increases 10 times, your output is reduced by 10 times. Your increased by 100 times, your frequency increased by 100 times, your output will be decreased by 100 times. So the smaller your output. So this is really what we call a low pass, like a low pass filter. Low frequency will get pass because it's 1, that gain is 1. But your high frequency gets attenuated. So if you have an input, in that case, say, I don't know, like a 1 volt input at a low frequency, and you have 1 put at a high frequency, and your low frequency output is 1, but your output frequency is, let's say, 100 times 0.01. So even though you have an input combined with a 1 volt low voltage, 1 volt high voltage, high frequency, 1 voltage low frequency, but your output is only low frequency passed to be 1 volt, the high frequency gets attenuated so much that it does not reflect much in the output. Okay, so that's a low pass. If we flip the R and C, you already know what it is. It's a high pass, which means I'm not going to go to details about this one, but just show you that. So this will go something like this. And this is your 3 dB. So this is 0 dB. This is your omega t, and this is minus 20 dB for decade, which means for high frequency, the things are going to pass 100%, 1, right? Up gain is 1 and 0 dB. But if your frequency is low, unfortunately, they'll be attenuated. So your output will be smaller. The lower the frequency is, the smaller. So in the future, you might see something like this. What is this? This can be called a bandpass, because in the middle, you amplify, but the low frequency gets attenuated, high frequency gets attenuated. And you have two, like 3 dB frequencies each on this side. And in the future, so this is 20 dB, but if you want output attenuated more, like, okay, it's okay, but it's too slow. I don't like, at this point, I don't want that much of output for high frequency. I want to filter a lot of them, like much more than like 20 dB decade. So you can, in the future, you will see something like this. I don't have space anymore, but I can do this. I can erase this so that I can have a better understanding for you guys. You can have something like this. You can have like, very high attenuation. Very deep, like even like very deep attenuation. So this way, and this can be more than 20 dB, maybe minus 40 dB per decade. So usually for stability, they have this, like 20, minus 40, minus 60, minus 80. So the more like attenuates more, so that would be better for your circuit. So much about the basic review of our low pass and high pass and so on as capacitors. So now coming back to our electronics. When you have a MOSFET, remember the structure of the MOSFET. The MOSFET was built with silicon. And silicon is a semiconductor device. So in order to get the current out of this semiconductor device, we need to put metal on each of the terminal, okay? Like we put body here, source, gate, and drain. So each one of them, we put a piece of metal. When you put a piece of metal, apparently what you're doing, you're forming a capacitor. Exactly. For low frequency, it doesn't matter because capacitor look like an open circuit. But for high frequency, the problem comes in because that little capacitor started to make a noise. The reason is that for modern MOSFETs, they operate at megahertz or even tens or hundreds of megahertz. Very little capacitor. Because the megahertz, 1 over omega c is the impedance. Because the omega is so high, a little bit of capacitor makes the largest impedance. Okay, so each one of this, between each of this plate is going to have a capacitor. So you see here between gate and source, for example, between here, this capacitor. Of course, you might say, oh, you have to be 2 parallel plates. No, you don't have to. Even 2 plates like this, they will have capacitance. It's just capacitance is smaller than if you have this. You have 2 plates like this, very big capacitance. You shift it, like you shift it like this, smaller, right? Because this is small. But if you do this, you do this, you do this, you do this, there's still capacitance, but just smaller. So you have this, and here, between these two, you have capacitance. And between this, you have capacitance. Between this, you have capacitance. Between this, you have capacitance. So all of a sudden, you have how many? 1, 2, 3, 4, 5 capacitance. Each one of these capacitance is going to play a big role in the high frequency region. So if you want to draw like the circuit, okay, what do you expect? How do they look like? I can draw here for you. is, remember our MOSFET initially was like this, right? So if you look at the circuit like this, okay, so there's capacitance between gate and drain, right? This is between gate and drain. So okay, we'll connect between gate and drain. And there's a capacitor between gate and source, right? So we connect that one. And but the problem with this drawing that they're showing the body instead of the actual source as a connection. So typically you have drain and a source, right? The current flow this way, but they have a body. So typically between drain and source, the capacitance, you see, between drain and source, ideally, I would connect a capacitor like this, right? Because there's drain and source, there are two plates. The one plate here, one plate here. But these two are so far. These two plates are so far that the capacitance between them is so small because they're very far. So therefore, this capacitance can typically be neglected. So then you might say, well, and then why you have like 4 or 5 here, but you only have 2 here then? The issue is that modern MOSFETs always have a body. And there's always a capacitance between drain and body, source and body, and gate and body. So the gate and body can be typically neglected, but the drain to body and source to body cannot be neglected. So therefore, there's something to body. So how do you connect the body? In your book, it does actually give you in chapter 5, it does have that connection is like this. The body is connected outside like this. So that's the body. But for most of the MOSFETs, oh, before I do that, so which means I can draw capacitance between here and capacitance between the body. So this is the body. This is the source, the drain, gate. So this is what you have between source and body and between drain and body. There's 2 capacitors. So now we have 4. See, 1, 2, 3, 4. We have 4 capacitors, all connected. You have 4 capacitors. But modern MOSFETs, most of them, the source and body are connected. So they actually connect this one and source. So if they are actually connected, that capacitance is gone. So that's the beauty when you can eliminate at least. So that's why in a lot of MOSFET drawings. So actually, I didn't do this, but remember the MOSFET symbol we use like this, but you will always see also MOSFET symbol like this. You'll see a symbol like this. This is the symbol is actually for the NMOS, means the body and the source are connected. So in this case, if you look at the big picture here, if source and body are connected, which means this capacitor is gone. So we only have 3 capacitors. So now, so this is actually the largest signal model or the symbol where we can place the capacitor. Then you can actually draw the small signal model. And then we can place all the capacitors, each of them. So this, most of this done in this chapter is the pi model. So in the pi model, if I draw the pi model actually ahead of that one, do you guys know how to draw the pi model already? So if you look at the pi model here, and if you go back to the previous slide, you have 3 capacitors we need to connect. And the capacitor between gate and drain can be easily connected over here, right? So that's what you see. Gate and drain is connected. And the capacitor between gate and the source can be connected right here. So you can see right away, it's no longer open circuit. When we analyzed this before, we always said, this is open circuit, don't worry about it, it's very simple. but now it's no longer because there's a capacitor over here. And then the capacitor between source and the body, right here, we didn't draw the body, but I'll tell you that in this class, basically we can neglect it. But just in case, we know what it is. So between source and body, you have another capacitor. So that's drawn here. And between drain and body, you have another capacitor, you have drawn here. But what happened is here, there's another one, GMB times VGS. So this current is induced because the capacitance effect in a MOSFET. But that current is very small. In fact, most of the time you can actually neglect it. And because if the source and body are connected, and then you can further eliminate this capacitor. So if you limit this one, well, actually, not only just eliminate, but this becomes a short circuit. So here, so all the things at the second hand, you see, it becomes all connected. So that's why we have this circuit over here. So we basically neglect the other current. That current we neglect it, and we neglect SP because again, source and body are usually connected. And then we have drain to body, gate to drain, and source to gate to source. We have 3 capacitors. So now you see this circuit. So ideally, if we have an input here, and you have output here, you can analyze the circuit and find the relation between VO and VIN, between VO and VIN. And then you can find the gain. So it's not that difficult because what you have, really, you only have like 2 nodes. So one node is here, and one node is here. So you have 2 nodes. You can write nodal equation very easily. But as you read the book, you will see that, well, the purpose to do that, even though it's simple, but it doesn't give you intuition of, okay, what does it mean? So that's where the book said, okay, let's do some simplification so that we can get the insights of the circuit. So to do that, the first step is that CdB, drain to body, is very small. Again, why we said it very small? Because this comparison to RO is fairly small. So if it's small resistance, I'll probably take this back. So what it means is that 1 over C dB times omega is much, much bigger than RO. So small CdB means large impedance. So if that impedance is much larger than RO, which means the 2 in parallel, the larger one gets neglected. Only the small one would count, okay? So if you have 1 in parallel is 100, how much is that? Roughly 0.999, okay? So that's why this one can be generally neglected. So if we generally neglect this one, now you only have 2 capacitor and a resistor. So the circuit is fairly simple. It's not a lot of, so this is where we further neglect this capacitance. Okay, we neglect it. Now, I will tell you, I don't think we have time today to get to the point, but by Wednesday, we'll get to the point. Even if we connect it here, we put it back, we'll see that the impact is fairly small. So that's why we can do it. So now we have this circuit. Even with this circuit, it's still quite complicated. How would you get the gain? In the sense that even though we can do small signal analysis, we can do this nodal analysis, but still the result will be quite a complex equation that does not give you a straightforward, like looking at, previously you get 20 dB or 3 dB, that sense you don't get it. So instead, we're going to do this two things here. So one is we're going to do what we call a short circuit current gain. So short circuit current gain. So when we do short circuit current gain, we basically have an input current, because we're not talking about current gain. So I think Wednesday we'll talk about voltage gain. So we have a current coming in, input current, and for the output, we short the circuit because we're talking about current. So we short circuit. So if you short the circuit, what happens? If we short circuit, is there any current? Is there any current through RO? No. Okay. So basically, short circuit, right? Short circuit. Okay. So if this is a ground, so this is 0 volts. So tell me, what is the voltage over here? What is the voltage at the up about the current source? How much is it? 0. Somebody says 0, right? Yes, 0 because it's a short circuit, so that's 0. Okay. So somebody might ask, how can you have 0 voltage there and 0 voltage here? You still have a current. It's okay because it controls the current source. Current source can have 0 voltage across it. Absolutely fine, no problem. Actually, you can get in real life. You actually can do that. Okay. So now, let me ask you. So what is the current over? Let me talk about a few currents over here. So let's call this I1. I'll call this I2. What is the current I1? Oh. What is the current I1? Can you tell me? Well, what I mean is, if you know VGS, how do we write I1 as a function of VGS? So it's VGS times S times CGS. Because 1 over S CGS is the impedance. So voltage divided by impedance is the current. So you got that. And what is the current I2? Well, to do that, what is the voltage between the GD? What is the voltage here? VGS. Yeah, because this is ground. That side is ground. The other side is VGS. So VGS, right? So then the current will be VGS times S times what? CGD. Okay, that's great. Okay, so now let's look at what is I input then. It's I1 plus I2, right? So it means it's going to be S. So these two add, we can get the S out, and we can get the VGS out, and we can get CGS plus CGD, right? Okay, so what is IO then? What is IO? IO is this way, which is here. So which is this current going down, and this current coming in. So which means IO plus this one equal to this one. So IO equal to this one minus the other one. So IO equal to GM VGS minus S VGS times CGD. So now we can have current gain, because AI equal to IO over II. So now the VGS is going to cancel. You see, VGS is going to cancel. So VGS cancel, we have S minus, no, not S. You guys can read it together with me so that you will remember this much easily. So it's going to be GM minus S times CGD over S CGS plus CGD. So we got this very simple equation. In this simple equation, typically S times CGD is much smaller than GM. So in this case, we always try to find things, but then we find, well, if you put this together, one is really too small. Usually 10 to 100 times smaller. So you really can neglect the other one. So if you neglect the other one, you will get this to be, so this will become let me redo this. I want to make sure that I'm S C G E. Okay, so we got this. We got this AI equal GM over S times CGS times CGD. And because this S can be replaced with omega, J omega. So this one now becomes GM over J omega CGS plus CGD. And if this whole thing, like the absolute value, becomes 1, y become 1. That's what we define. We call it unit gain. So if this whole thing is becoming 1, and then our current gain is 1. 1 is means unit gain. So current one, this becomes 1, which means omega equal to. So omega equal to this over GM. So we have if A, we have omega equal to CGS plus CGD. Oops. No. We're going to get this omega equal to GM over CGS plus CGD. And right. So if we get this one here, our gain, unit gain is 1. So our basically our circuit has a unit gain of 1. And then this frequency we call it omega t. I call it omega t. And for so for BJT and MOSFETs, we're going to have this omega t. What this really means is that we're going to talk about this on Wednesday. We're going to look at what it really means. What it really is that this thing is going to be like this. Let me see if there's a circuit here. Yeah. Yeah. So it's going to be something like this. And this is your frequency that we're going to talk about on Wednesday. So in your homework, the very first couple of homeworks is trying to find FT. Well, FT is apparently omega over 2 pi, right? So it's the same thing. You need to find omega t, and that is that. Okay, so let me close this lecture, and then we're gonna go over to our quiz. So you guys have the quiz already open. The password is